She just said like she doesn't know how she's doing it yet, but she said like we've changed from B students to A students, so hopefully because we changed so much, she's like I'm not gonna hold you guys like for a whole semester. That's what I'm hoping.
All right. Could I ask a favor, actually? Um, I think I have everything set up. I think I'm online. If actually anyone's online and listening, can you just send me a message in the chat if the volume is okay? And if someone here actually can join online just for a sec, just to see if you can hear through the speakers. I see there's 6 people live, but nothing yet in the chat. So if you could just put something, just make a comment. I'd hate to get halfway through and realize none of this got recorded. It, there's a delay, is there? Okay, perfect. Okay, so probably I won't get any comments in the chat until 15 seconds later anyway. I think we're okay to start then. All right, folks, so welcome to our first tutorial in a series of tutorials for the final exam. We have 3 of these, and this one will be available online afterwards. So the same link that I sent out this morning, you can just click it again later, and it'll just show you a recording of the same thing. And I will timestamp it for each question, so if you want to go through them again, you don't just have to scroll and kind of guess where I am. Okay, so the first set of questions here are around the IUPAC naming, which is something that we didn't spend any time on in class, but I made a video tutorial that I posted up. There was a bonus assignment based on that, and there will be bonus questions on the exam based on this too. So to give you a little more practice, we decided to give you some more example problems here on the mock exam. One thing I'll say is this mock exam is way longer than the actual exam. Like, yeah. It's like double in terms of the number of questions, but even the questions on the mock are a little longer on average than the ones in the exam. And I know because when I went through these to solve them, yeah, there's like the long version of every question is on here. So this is great practice if you get yourself through the mock exam and can answer all the questions without help. You know what I mean? And by without help, I mean without going and checking resources midway through. You'll be in great shape for the final exam. No surprises. We're going to serve it straight up pretty well. So this question on the mock asks for the IUPAC name for each of the following molecules. And so what we have to do first of all is identify what the functional group is that we are dealing with here. And in this first one, A, we can see, where is my, well, I'm going to need ink here. I see my problem. I didn't put it in Notability, I don't think. More. Open in another app. I don't want it in this app. I want it in Notability. Yes, good. Now I can actually use my pencil, which is important. Okay, so first thing we need to do is identify the functional group, and we have here a carbon-carbon triple bond, which makes this what kind of compound? Or you guys just want to listen. You don't want to have to interact. That's fine. It's an alkyne. Carbon-carbon triple bond is an alkyne. So what we need to do is identify the longest carbon chain that has the carbon-carbon triple bond. And so that would be kind of going 1, 2, 3, 4, 5, 6, 7, 8, which is an octyl chain. So the base name for this chain is octane. Because we have a triple bond, it's an octyne. So the end of this is going to be octyne. And then you have to look and see what else is attached to the chain besides the octyne. And we see on carbon 7, there's a chlorine. So this would be 7-chloro-octyne. And we numbered it the way we did because we want to give the lowest possible number to the carbon-carbon triple bond. The next one, we have a carbon-carbon double bond, which is an alkene. Oh, yeah. Look, I made a mistake on my very first one. 7-chloro-3-octyne. Great. 0 for 1. We'll get better. This one's the alkene, so this we have to find the longest carbon chain that contains the double bond. And what we want to do is number it in the direction that gives the lowest possible number to the double bond. So that would be starting from the left, where we go 1, 2, 3, 4, 5, 6, 7, 8. This is also an octyl chain, but this has a double bond, so it's an octene. What else is attached? On carbon 4 and carbon 5, we have alkyl groups. And we want to order them in alphabetical order when we write out the name. And if you look at the ethyl group, the ethyl is 2 carbons long. This is 1 carbon, so that one's the methyl, because the base name of that chain would be methane. And so that means we would have the full name of this being 4-ethyl dash 5-methyl dash 1-octene to give the position of that double bond. Next one, we have an alcohol. And again, we have to find the longest carbon chain. And sometimes we're a little tricky here. But this one is not written out in a straight line like it was in the other examples. And that has 1, 2, 3, 4, 5, 6, 7 carbons. Is hept. And this has an OH on it, which means it's an alcohol, so it's going to end in heptanol, OL. And what else do we have attached besides the OH? We have an ethyl, again, on, if you start counting from the left, 1, 2, 3 on the 3rd carbon. If you start counting from the other direction, 1, 2, 3, 4, 5, it's on carbon 5. Now what we want to do is number it in the direction that gives the lowest possible number to the OH first. The OH is in the name. The OH, what we say, gets priority. So we want this one to be, but it doesn't actually matter which side you start from for the OH. It's going to be 4 no matter what. So if it doesn't matter for the OH, we move on to the next one, which is the ethyl, and try to give it the lowest number. So that way the lowest number we can give the ethyl is if we give it the number 3. And then the heptanol, we put the 4 to show the position of the OH. And we end up with 3-ethyl 4-heptanol. The next one is just an alkyl halide. So halides are atoms that are in group 7, or 17 actually, of the periodic table. They changed the way they number it. So chlorine, bromine, iodine, fluorine. And we don't include them in the base name of the chain. We include them as if they're attached to the chain or as if they're substituents. So what we would do is find the longest carbon chain, which looks like that, which is pentane. And then we list all of the things that are attached. So we have to number this to give the lowest possible number to the first substituent. If we start from the left, the chlorine gets number 2. And if we start from the right, the bromine gets number 2. So it's a tie. So what we do is we kind of like cross them out and then start again looking for the next substituent. So if we cross out a chlorine and a bromine and start again, starting from the left, the second chlorine comes at carbon 2. But starting from the right, the next thing you hit is a methyl on carbon 3. So we want to give the lowest possible number to the first encountered substituent. If it's a tie, you want to give the lowest number possible to the second encountered substituent. Yeah.
What did you say this group was called?
This is just an alkane with halides attached, so we call it an alkyl halide. Yeah. All right, so basically we have pentane and we have 2 chloros and a bromo and a methyl. And we're going to number it starting left to right to give the lowest possible number to the second chlorine. And so what that gives us is we're going to write them alphabetically. We do the bromo first because B is first. And then we have the 2 chloros. Chloro comes after bromo. And that becomes 2,2 dichloro. And I can see already I'm going to run out of room here. So I'm going to erase the pentane for now. Keep going. We have a 3 methyl pentane. And just a note, methylpentane is one word. There's no space between the methyl and the pentane. It's just all written out all at once. Yeah. Cool. Makes sense.
So the wrong goes first, even though it's crossed out first?
That's right. So you when you write out the name, you list the different substituents in alphabetical order, not in order of their numbers.
Okay.
Yeah. So there's a lot of like kind of small complicated rules to this. We're actually only giving you a very small subset of them. The actual rule book is like 200 or 300 pages. So yeah, we're kind of giving you a. This will work for most commonly encountered compounds. I'll say that. Yeah. All right. So the next one has an NH2. What kind of functional group has an NH2 on it? Remember that one? That one's an amine. An amine is just a nitrogen attached to a carbon with other carbons and hydrogens around. So that one has the longest carbon chain, will be the one I circled right here, which is 5 carbons, which is pentane. And on carbon 3, we have an NH2. So we have to identify the position of the amine group, the NH2. So that would become 3. Pentan, and what we do is we cut the E off and write amine at the end of the word. So it's pentanamine, like that. So we kind of have one example of each of these as we go through. The next one is an oxygen with a carbon attached on each side. Any guesses for that one, what it's called? That one is an ether.
And it has like an O on one side, that like an ester, and while ether is the one with something on both sides of the O.
If on both sides of the O, if you have a carbon double bond oxygen on one side, that's an ester.
Okay.
Yeah, and we'll see those in a sec. So in this case, we have the oxygen, and the way we do those is we take the shorter chain, and we consider that as a substituent of an alkane. So the longer chain here is 1, 2, 3, 4, 5, 6, 7. So that's a heptane. And then we look at the ether chain that's attached, and it has 3 carbons, so it's a propyl chain. But with the oxygen there, we call it a propoxy chain. So it's like a propyl oxy, which is shortened to propoxy. And then we say there's a propoxy chain on this heptane, and we have to give its position. And its position is on carbon 3, which is 3. Propoxy heptane is one big word. Sound good? Next one, we have an SH. These are thiols. Well known for being very bad smelling. Skunk spray is thiols, a mixture of different ones. Kind of have like an eggy smell to them. This one you can see we have to find again the longest carbon chain, which we can say is this one. Longest carbon chain without branching, like longest carbon. Did you ever play, what's that game with the trains? You have to get the longest road. No, longest road is a different game. That's Catan, yeah. Settlers of Catan, or Catan, or whatever. Ticket to Ride is what I'm thinking of. And you also have to have the longest continuous route. Yeah. So I'm confusing two games. But the principle is the same in both of them. Same in organic chemistry. You want to find the longest carbon chain. You don't want to double count anything. And yeah. So in this case, we have 1, 2, 3, 4, 5, 6, which is a hexane. That will be the base chain here. And then you look to see what's attached. We have our SH, which makes this a thiol. We have a methyl here, a methyl here, and a methyl here. So this is going to have a trimethyl. And what we want to do is give the lowest possible number to the SH, because it's part of the name. And we do that by starting from the left. And that would put number 2 where the SH is. Okay. So what this name is going to be called is going to be a hexane thiol. Not a very inventive name for it. It's hexane with a thiol on it. And we have to give the position of that, and that's going to be on position 2. And then we have to say how many methyls we have, which is 3, and their positions, which there's another one on carbon 2, and there's 2 of them on carbon 5. So this would become 2, 5, 5 trimethyl 2-hexane thiol. Sound good? All right. Online people, you can hear me okay? Feel free. Oh, I see from Cassidy. Thanks. Volume is perfect. If you have any questions online too, you can put them in the chat, and I'll see them 15 seconds later. All right. I have some more of these. H, we have, it looks like a normal alkane, except in the middle of the chain, we have this carbon double bond oxygen. And that group, carbon double bond oxygen, is called a carbonyl group. And a carbonyl group appears in a lot of different functional groups. It's in ketones, it's in aldehydes, it's in esters, amides, a whole bunch of them. So in this case, because we have a carbon on both sides, this one is a ketone. Okay, a ketone has carbons on either side. So what we want to do is find the longest carbon chain that has the carbonyl group on it, which we can start from the left. And it looks like that. And we want to number it in the direction that gives the lowest possible number to the carbonyl group. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this has 9 carbons. This is going to be a nonane, but because it's a ketone, it's going to become a nonanone. So it's a little fun to say, but there we go. So this is going to become a nonanone, which is a nonane with the E removed, and we add ONE, and the ONE means it's a ketone. Okay. So when you think about compounds that you might be familiar with, like Tylenol, it ends in OL. Tylenol suggests that it's an alcohol. Now, don't take that literally always, because sometimes medicines just pick names that sound chemically, that the name is actually not correct. But sometimes it's actually really good. Like ibuprofen is a good one, because ibuprofen has an isobutyl group, which is IBU, and the pro, it has a propionic acid group, and the phen is because it has a phenyl group. So like literally the name is just the pieces that make the molecule. Think about a Toblerone bar. Toblerone should be a ketone, right? Ends in ONE. All right, we got to give the position of the nonanone, which is position 4, and then we have a bunch of methyls. We have 1 on carbon 2 and 2 on carbon 8. So this becomes 2, 8, 8. Trimethyl. We have to put tri if there's 3 of them. For nonanone. Fun to say. Structure I. There's something wrong with structure I. Structure I is missing something. Any guesses? There has to be another hydrogen on that nitrogen. I don't know if you noticed that. My organic chemist eyes zoom in on that missing atom. When we draw bond line structures of things, we typically don't draw hydrogens if they're on carbon, but if they're on non-carbon atoms, we have to draw them. So if they're on oxygens or nitrogens. So that hydrogen has to be in there. If there was no hydrogen there, that would have to have a charge. And it doesn't have, so something's missing no matter what. If you have a nitrogen attached to carbon, normally that's an amine, but in this case on one side of it, it has a carbon double bond oxygen. And that makes this a similarly named amide. Amides are super important in biology because those are the functional groups that hold together amino acids to make protein chains. So in biochemistry, we often call these peptide bonds, but in chemistry we call them amide bonds. Actually, there's a slight difference between what a peptide bond and an amide bond is in terms of what atoms are included in each, but I'm not going to get into that for today. So this is a 1, 2, 3 carbon chain that leads to the amide. And there's nothing attached except on the nitrogen, you see there's a 2 carbon chain, and this carbon chain that's attached is an ethyl. And the way we indicate where the ethyl is attached is by putting N in front of it. Yes, question?
So what is the most defining thing about amide?
It has a nitrogen attached to a carbon double bond oxygen. So you see the carbonyl group there, and then there's a nitrogen attached to it.
Yeah, this was like a carbon, like then nitrogen.
Yeah, if it was just a regular carbon with no double bond oxygen, it would be an amine. So this one gets the name N-ethyl because we just put N to indicate the position of where that ethyl is. It's on the amine, it's on the nitrogen. Prop. And we're going to write propane, but this is an amide, so you drop the E and write amide at the end of the name. Propanamide. Okay. Next one, we have a carbon double bond oxygen with a carbon on one side, but a hydrogen on the other. So that being the case, this is an aldehyde. So the aldehyde, we have to number the longest carbon chains, and we want to give the lowest number to the carbon double bond oxygen carbon. That goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that one would be decane. But for aldehydes, we end them with al. Kind of like an alcohol is OL. This becomes AL. Decanal. Decanal. I guess is how you'd say that. And the next one that we have is we call this one an ester. You have a carbon double bond oxygen attached to another oxygen. So like we have that carbonyl group, and what's attached on either side has huge impacts on how it reacts, what its properties are. In this case, it's an oxygen. It's sort of like an amide, except instead of a nitrogen, we have an oxygen. And the way we do that is the base chain of this molecule is not the longest one. It's the carbon chain that has the carbon double bond oxygen. And this has 2 carbons in that chain. So this becomes an eth group. And the way we name an ester is we want to go do ethane, but we drop the E and we end in 08. ethano8. And then for the other chain, that has a 1, 2, 3, 4, 5, 6, which is hexyl. And so we put hexyl in front. Hexyl ethanoate. And there is a space between those two when you write this name out. It's not hexyl ethanoate all at once. It's hexyl ethanoate. This is a lot when you do them all at once, like just blitz through them, isn't it? But of course, you all spent a few hours watching my tutorial several times, letting all that information sink in, and hours practicing the practice assignment on it. So this is just like icing on the cake, right? Yeah, not too bad, not too bad. All right, last one. Carbon, double bond oxygen, carbon on one side, OH on the other side. This is something new again. What's that? It's not an ester, it's not an amide, it's not a ketone, it's not an aldehyde. This one is a carboxylic acid. ACID. As the name suggests, it's an acid. That's because you can draw resonance structures of the conjugate base if you take H plus off. If you remember resonance structures, it stabilizes ions, structures, yeah, good stuff. That's first semester. Carboxylic acid, and so what we want to do is find the longest carbon chain, and we want to give the lowest number to the carbon double bond oxygen once again. General rule of thumb, carbon double bond oxygen, it will always want to have the lowest number. Since it's at the end of the chain, and it has to be at the end of the chain, it will always have the number 1, 2, 3, 4, 5, 6. So we have a bromo on carbon 3, 2 methyls on carbon 5 that are not part of the main chain. And so we would list those out alphabetically. Bromo coming first, 3 bromo, 5, 5 dimethyl. Note when you're naming these things, the di or the tri that come there, that is not counted in the alphabetization. It's the methyl versus bromo, B versus M. So we just kind of ignore the prefix, which is weird, but that's how it's done. And then we have our long chain was, I think we said 6 carbons. And so normally we would write hexane, but here we're going to write hex, and we're going to drop the E, and carboxylic acids end in oic acid. Hexanoic acid. There we go. We squeezed it in. Great, we're done with naming. Half an hour, question 1 complete. So here we go. We'll go through a little quicker through maybe some of the other ones. This one wants us to identify the different functional groups that are on this compound. This we'll do really quickly. A is a ketone. It's a carbon double bond oxygen with carbons on either side. B is an alkene. When you go in and you end up taking organic 2, A and B together like that actually makes a functional group called an alpha beta unsaturated ketone. Which, yeah, remember that when you take organic 2, as you all probably will. C has an OH group on a carbon, no carbonyl group in sight. That's an alcohol. We call this actually a secondary alcohol because the carbon with the OH is bound to 2 other carbons. D is an amide, which is a nitrogen attached to a carbonyl group. And that nitrogen is attached to 2 carbons, so it's also a secondary amide in this case. Great, 2 was quick, a lot quicker than number 1. 3, identify the functional groups circled in each of the following. What's A? Does anyone know any of these? You can throw out, like, give me one of the letters and what it is. Not interested. That's okay. I don't want to put anyone on the spot. This one's an ester. Molecule, by the way, is aspirin. Here's a bonus one. That's a carboxylic acid. Okay. This one is an amine on B. C, that's an aldehyde. D, it's an ester. This is a carboxylic acid as well. I'm just going to abbreviate that. So that is a carbon double bond oxygen carbonyl group attached to an OH. F, carbonyl group, oxygen, and another carbon over here makes this an ester. This one is an alkyl halide. This one has an oxygen with carbons on either side. So that one's called an ether. When you see these rings like that with a circle in the middle, that's the same thing, by the way, as alternating double bonds. Because there's resonance structures that you can put them in either place, we sometimes just use a ring. Either way, that's an aromatic ring. And over here, it looks like we have an alkene hiding up there as well. In this case, we have an amine. And that nitrogen is attached to 3 different carbons. One here, and one here. So that's a tertiary amine. I think that molecule is nicotine. It's funny when you do this long enough, you recognize the structures and you know what the molecule is. It's made out of. This one here is a molecule called anethol. And it's the compound in licorice that gives it that licorice flavor. It's in like sambuca and ouzo as well. In fact, it's not very soluble in water. So if you take sambuca or ouzo and you add like ice to it, it like turns white and cloudy. And that's because that anethol oils out, so as we say, it becomes insoluble, and then you get 2 phases. So yeah, it's a good trick. You can explain to your friends why you don't drink it on ice. All right, question 4. Now we're doing some actual calculations here. Chlorine dioxide reacts in basic water to form chloride and chlorate according to the following chemical equation. Under a certain set of conditions, the rate of disappearance of chlorine dioxide was determined to be 2.3 times 10 to the minus 1. What's the initial rate of appearance of chlorite ion under these same conditions? All right, so another way of kind of writing this out is you could say that delta, it's ClO2 that's changing, concentration of ClO2 over delta T is equal to negative 2.30 times 10 to the minus 1 molarity per second. And I have the negative in front of it because it's disappearing. We know it's on the reactant side and it's going away. So its rate of change of concentration is negative. It's going down. And we want to know the rate of appearance of the chlorite ion. And so the chloride ion we know is appearing, so its number has got to be positive. And the way I would look at this is I would consider it to be kind of the same as if we were doing stoichiometry and you had 2 moles going to 1 mole. The rate is going to be 2 going to 1. So in other words, what I would write would be the change in ClO2 minus over the change in time is going to be equal to, first of all, negative 1, because this one is going to be appearing. Negative 2.30 times 10 to the minus 1, molarity seconds to the minus 1, times the prefix in front of the one you're converting it to, which is 1, divided by the prefix of the one that you're converting it from, which is 2. So you're going to be multiplying that by 1/2. The negative and the negative will cancel, and the number you should get is 1.15 times 10 to the minus 1 molarity per second, or molarity seconds to the minus 1, or moles per decimeter cubed per second to the minus 1. Lots of different ways to express the same unit. People good with that one? First ones aren't too bad. What are the units of K in the following rate law? The way I think about things like this is rate is always in the units molarity per second. That's always the unit for rate. And some people like to memorize all the different possible units for K depending on the order. I don't. I just like realize that it always have to be molarity per second. So we know that concentration is in molarity. So this is going to be molarity squared, which is equal to molarity to the power of 4. And so the units for K have to multiply by molarity to the 4th to give you molarity per second. So I would say, well, this has to be molarity to the minus 3 per second, because that times molarity to the 4 equals molarity per second, which is what we always need to get for rate. Cool. So I'd advise against memorizing. Just realize you can calculate it, you can figure it out every time.
Isn't it m minus 3 s minus 3?
M minus 3, S minus 1 is the same thing. So yeah, you could also write this out as M minus 3, S minus 1.
Might as well get the exponents to see 2 to the x4.
Yeah.
3 and s minus 1. So it does minus 1.
It could be confusing. My daughter's in IB, and they always write molarity as moles dm minus 3, which you get used to after a while, but like, yeah, we don't really use cubic decimeters very much. Like, can I have a cubic decimeter of water, please? I don't know. IB is international, so they do what they think the world needs. Okay, we have this same reaction again, chlorine dioxide reacting in basic conditions to form chlorate and chlorite. And so this is one of those initial rates methods things where we have to find out the rate law for this particular reaction. And they want the rate law, and they also want the value of the rate constant K with units. So I kind of like these questions because every one of them operates the same way. Once you kind of know how to do these, they become pretty straightforward. We always start by writing out the rate law like this. Rate equals K times the concentration of the first reagent, ClO2, the power of X, times the concentration of the second reagent, which is hydroxide, the power of Y. And when you do these kinds of questions, the X and the Y has nothing to do with these coefficients in front. Just ignore those coefficients completely. They are not important for doing this reaction, or this question. There's two ways to do this. One is by what we say inspection, where you look at the numbers and you see how the rate changes when you change a concentration, and you realize what the number should be. Or there's a calculation way to do it, which takes a little longer, but it requires less brain power. So I'm going to use the less brain power way because I want this to be clear. It's hard to explain how to do it by inspection if you find it hard to see. So for X, we're going to do X first, which is the exponent for the ClO2. And what we need to do in that table is find two experiments where the ClO2 changes, but the hydroxide stays constant. So we don't want anything on the hydroxide thing changing. We just want the two ClO2 changes. So if you look at experiment 1 and 2, the concentration of hydroxide there is constant, while that one doubles. So we can use experiment 1 and 2 to find X. So what we're going to do is use the equation X equals ln rate 2 over rate 1 over ln concentration of A2 over concentration of A1. And that's on your formula sheet. That's the mathematical way to solve for A. And it doesn't matter which one you pick as 2 or 1, as long as you're consistent. So rate 2 has to go with concentration 2. Okay, so let's call experiment 1, 1, and experiment 2, 2. Which means this is going to be the natural log of rate 2 which is 2.30 times 10 to the minus 1 molarity per second, over experiment 1, 5.75 times 10 to the minus 2 molarity per second, divided by natural log concentration of ClO2, 2, which is 0.100 molar, divided by 0.0500 molar. That actually equals ln 4 over ln 2. Often it'll simplify out like this, and that equals 2. So that means that x up here is equal to 2, and we are done half of the problem, the first half. Now we got to do the same thing for y. For y, we're going to, let's pick, we got to find the two experiments. Experiment 2 and 3 has ClO2 constant with hydroxide changing. So let's use experiment 2 and experiment 3. And why don't we pick experiment 2 as 1 and experiment 3 as 2? That will give us natural log 1.15 times 10 to the minus 1 over 2.30 times 10 to the minus 1. Both of these are molarity per second, which will cancel out. Divided by natural log concentration of hydroxide 2, which is 0.0500 molar, divided by 0.100 molar, equals ln of 0.5 over the ln of 0.5, which is equal to 1. The inspection way to look at that would be to say, well, when ClO2 is constant, hydroxide is cut in half, and the rate is cut in half. And if the rate changes the same way the concentration changes by the same factor, then the exponent has got to be equal to 1. So that's something that sometimes you can see. It's easy to see sometimes if it's a whole number, like x equals 1 or 2. But sometimes x is like a weird number, like 1.5 or 2.66. And in that case, it's really hard to see that, and you have to use this calculation method. Or I should say, it's easiest to use the calculation method. Yeah, that's a question.
Basically, you want the, for the value that you put into the equation, you want the smaller value or the larger value?
Doesn't matter. You can have the smaller over the larger or the larger over the smaller as long as you're consistent. In other words, the rate that you chose to put on top here has to match or be from the same line as the concentration you have on top on the bottom. So if we said instead the other way around, what you'd end up with was ln 2 over ln 2, and that's also equal to 1.
I just guess for someone else, something like bigger over smaller values.
Yeah, no. Always make sure that whatever's on top on both the, in terms of the rate and the concentration, they both have to come from the same line. We're not quite done. We have our rate law, sort of. Rate equals K times ClO2 squared now, times the concentration of hydroxide, like this. But we don't have the value for K, and it specifically asks us for the value of K down here. So all we need to do is feed in the values of concentrations and rates from any one of those 3 experiments. So to do that, I'll pick, why not experiment 2? Doesn't matter, you can pick 1, 2, or 3. I'm going to pick 2 only because when I look at those concentrations and they're both there at 0.1, it looks like the calculation might be a little bit easier for us to do. But it doesn't super matter. K is what we're trying to solve for, so that's going to be equal to the rate divided by ClO2 squared times hydroxide, like that. And the data from experiment 2 from the table, 2.30 times 10 to the minus 1 molarity per second. This is 0.100 molar squared, 0.100 molar. And this gives you units of, or value of, 230. Now I got an eraser. I'm going to make it look better than that. 230 m to the minus 2, molarity to the minus 2, seconds to the minus 1.
And then, does it state the concentration for different ones?
Sorry?
The, above and down question, does it state the concentration of both for different ones?
Yes, they were both 100, as you can see right here. And it doesn't matter. You could pick experiment 1 or 3. It'll give you the same number.
As long as you even add the same experiment.
Yeah, as long as you're consistent and use all the same numbers from the same experiment.
Okay. Okay, so the 1 and 3 really.
Yeah. All right, 7. The rate law for the rearrangement of CH3NC to CH3CN. I think that's called an isonitrile to a nitrile, which are functional groups I don't think you guys learned, but they are both functional groups. There's a lot of functional groups you didn't learn yet, but you'll get to them. Especially in biochemistry. There's a bunch in biochemistry that live in cells. Okay, the rate law is determined to be this thing here. And we can probably tell from that what the order is. Is this 0 order, first order, or second order? It's first order, right. Okay. So if the order is equal to 1, then we have an equation for the half-life, which is the natural log of 2 over k. So it wants the half-life, and it gives us k. This is actually pretty straightforward. It's ln 2 over seconds to the minus 1. Ln 2 is 0.693. And that gives us 5.33 times 10 to the minus 4 seconds. Straightforward, right? The tricky part here is identifying the order correctly. And that's just going to be the sum of all the exponents. And there's only one thing there, and its exponent is assumed to be 1 if we don't show it. And as long as you pick the right order and you pick the right equation for the half-life, the actual calculation part is easy. It's picking the right one that's the hard part. If you picked it for the second order, it wouldn't work. Although, I guess there's some hidden information in this question, because both 0 order and second order equations have the initial concentration as part of the half-life equation. And we didn't give you an initial concentration. So there's only one of the 3 formulas for half-life that you have enough information to solve. So I don't know. Look for little clues and hints like that on the exam too. We tend not to try to overwhelm you with useless information. The only useless information you kind of get is for equilibrium constants. We almost always give you the temperature, whether you need it or not. And the reason is because equilibrium constants are only correct at a given temperature. So they're often presented together. Not because you need to use the temperature in your calculation. All right, question 8. The reaction A plus 2B to products was found to have the rate law K equals A times B squared. Predict by what factor the rate of reaction will increase when the concentration of A is doubled and the concentration of B is also doubled. Okay, so rate equals K times concentration of A times concentration of B squared. If concentration of A is doubled and concentration of B is doubled, the rate will increase by times 2 for doubling A, because the exponent is 1, and times 2 squared for B, because the exponent is 2. So basically what you have is 2 to the 1 times 2 to the 2 equals 8. So this will increase by a factor of 8. Make sense? Those ones aren't too bad. Question 9. This reaction follows second order kinetics. Key piece of information. And we're saying that the concentration of NO2 drops from this value to that value. So this would be our initial concentration, and this would be our final concentration, A. And it happens in 100 seconds, and that's our T. What is the rate constant K at this temperature? So what we need to do is get the integrated rate law for this particular reaction. And we need to pick it for the right order, which is second order. And that integrated rate law looks like this. 1 over A equals KT plus 1 over A0. And that's the form it appears on your formula sheet. The only thing on your formula sheet, it doesn't say that it's second order. There's 3 of them there, one for 0 order, one for first order, one for second order. So you got to pick the right one. It has 2 different ones for first order. Well, it's the same equation, they're just rearranged forms. Yeah. So a life tip for you here. The front page, the formula sheet you'll get is on Acorn right now. It's the same one you will see when you're sitting in your final exam. Make sure you can identify on that formula sheet which of those equations belong to first order, second order, and 0 order.
Same as the,
It's the same one we'll be using all semester. Yeah.
yeah, okay, I'm like,
Yeah.
never able to print it off and like scribble all over it. I was like, I had to make a new one.
Yeah, we didn't change anything on that. So it's the same one you should be used to. So yeah, just make sure that you can identify the right one. This is the right one for second order. And we are asked to find K. We can rearrange this, I guess. This is going to be 1 over A. Sometimes you see it A at time T. Minus 1 over our initial A divided by T is K, which is equal to 1 over our initial concentration is our concentration at time T is 0.016 molar minus 1 over 0.10 molar divided by 100 seconds. And if you calculate that out, you get 0.525 molarity to the minus 1, seconds to the minus 1. Or I guess if you were worried about sig figs, we should really only have 2 sig figs. .53, if you want to be rigorously correct. 10, the graphs below all refer to the same reaction. What is the order of this reaction? So here's something else you should be able to do is identify what type of graph. And the one I would look for is which one gives you a straight line, what you have to plot versus what to give you a straight line, depending on the order, with the only 3 options being first order, second order, and 0 order.
Is the order of second 0 first?
Is what?
Is the order of second 0 first?
Whatever. Yeah, I think however you remember it. So the one I would look for here is the one that's a straight line. And this one gives concentration versus time as a straight line. That's negative. In other words, the rate is always the same. The rate of change of concentration doesn't change throughout the reaction. So this is a 0 order.
Because just concentration is 0, ln concentration is first, and 1 over it.
Yeah. That's right. So yeah, for first order, you would have ln A versus T is a straight line. And the other one, I think, what is it? Ln A versus 1 over T? This is first. And 0 is just A versus T, which gives you a straight line. And 11. 11, here we go. The activation energy for the following first order reaction is 102 kilojoules per mole. The value of the rate constant, there's really only one equation that you get that uses activation energy, and that's the Arrhenius equation. So the Arrhenius equation, there's actually 2 forms of it that we often use. One is one that looks like this. K equals A to the E to the minus, that's a minus here, minus EA over RT. And there's the other form where you have 2 temperatures and two rate constants. And that looks like this. Ln K1 over K2 equals minus EA over R 1 over T2 minus 1 over T1. So in this particular case, we are given the value of the rate constant at 35 degrees, and then it gives you a new temperature, and it wants the rate constant at that temperature. So this is the form we want to use over here, the two temperatures, two rate constants, one. A couple things we need to do here is EA and R are going to have to be in the same units. So R, we typically use 8.314 joules per kmol. And because that's in kilojoules, we'll want to turn that into 102,000 joules per mole. The other thing we want to do for this is not use degrees Celsius. We want to use Kelvin. So we want to convert our temperatures into Kelvin. 0 becomes 273 Kelvin, and 35 degrees becomes 308 Kelvin. Like that. All right, so let's do some math here. We could say that ln K2 over K1 is minus 102,000 joules per mole divided by 8.314 joules per kmol times 1 over 273K minus 1 over 308K. And that equals negative 5.107. We can get rid of the ln on the left by raising each side of the equation, the power of e. So e to the ln K1 over K2 equals e to the minus 5.107 equals just K1 over K2 equals 0.00605. All right, so what do we use up here? We used our T2 was at 0 degrees. So this is K2 and T2. This one is K1 and T1. So basically what we want here is K2. K2 is our unknown. So K2 is going to be equal to K1 divided by 0.00605 equals 1.35 times 10 to the minus 4 I think I messed this up. I did mess this up. And here's how I messed this up. I'm going to go back and fix this. My equation is K2 over K1. That's why this isn't working for me. So this becomes K2 over K1. You can see how it's easy to make a mistake like this when you have a lot of calculations. K2 over K1. And then what we have over here is K1 times 0.00605 equals 1.35 times 10 to the minus 4 seconds to the minus 1, 0.00605, which is unitless. And that gives us the number 8.17 times 10 to the minus 7 seconds to the minus 1. So a little bit of work to get us there, but there it is. Okay. How's everyone doing? So far, so good? We're an hour in, and we did the bulk of it. Number 1 took a long time. We'll get through this a little quicker. Question 12, the first order decomposition. First order being important. of carbon-14 is a first-order reaction with a half-life of 5720 years. If 75% of the carbon-14 in a piece of wood is decomposed, how old is the wood? I would look at this as a first-order integrated rate law kind of question, where we would use the equation concentration of A is equal to concentration of A naught times e to the minus kt. That's the first order integrated rate law that you find on the formula sheet in front of your exam. And we need K. We want to know T. How old is the wood? That's what we want to know. It doesn't actually give us concentrations of anything, but one thing that we know is that 75% of the wood has decomposed. So that means like there's 25% remaining, right? So what we can say here is like 0.25 equals 1 times e to the minus kt. Or another way of saying that is concentration of A over concentration of A naught equals e to the minus kt equals 0.25. But to solve for T, we need K. And to get K, we're going to use our half-life. T1/2 equals 5720 years equals natural log of 2 over K. So K, I'm going to come down here, K equals natural log of 2 over T1/2 equals natural log of 2 over 5720 years. And that should give us the number 1.21 times 10 to the minus 4 years to the minus 1. We don't need to convert this to seconds. We're good with years. Okay, so from above we had e to the minus kt equals 0.25. We can say that that's equal to e to the minus 1.21 times 10 to the minus 4 years to the minus 1 times time. It's up in the exponent there, so to get rid of the exponent, we can take the natural log of each side. We can say that the natural log of 0.25 is equal to minus 1.21 times 10 to the minus 4 years to the minus 1 times time. Time is equal to natural log of 0.25 divided by negative 1.21 times 10 to the minus 4 years to the minus 1 equals 1.457 years, which is way more sig figs than you could ever actually get from a method like this. So I'm going to just say that that's 1.1 times 10 to the 4th years. Okay? Scroll up. The 0.25 comes from the fact that 75% has decomposed, so 25% is still remaining. Yeah. And so 25% is the 0.25.
Just using something like just the two brackets, not declaring the e into something on the side. Usually just
Yeah. Yeah. So I would say here, common mistakes, forgetting to, like just putting 75% straight in would give you the wrong number. An easy way to do this, and sometimes there's shortcuts to questions like this, is realizing that 75% complete is 2 half-lives, right? Because going to 50% is the first half-life, and then 50% of that will get you to 75%, so it's 2 half-lives. So all you really need to do is take 5720 and multiply by 2, and you're all done. So yeah, if you see things like that, especially in the half-life ones, we often like to give you questions where they're like, you know, if I gave you the same question and said, if 50% has decomposed, how long will it take? You can go through this whole song and dance that I did here. It'll always work, but you can just say, oh, it's 1 half-life, 5720. But if it's a weird number like 29.4%, you can't really, you know. All right. We're doing good. Another sheet complete. Question 13. Decomposition of ammonia in the presence of tungsten. Plot of concentration of ammonia versus time yield a straight line with that slope. Okay, so that's going to look like this. And let's make it purple. Where what we have here is concentration of A versus time, and this is the slope right there. If Dr. B started with an initial concentration of 1.5 molar, what would the concentration be after 5 minutes? Okay, so that's the question that we're looking for here. We need to recognize what the order is first of all. This is going to be an integrated rate law question, but you're not told the order. You have to figure out what the order is based on there's two pieces of information that can give you the order here. One is the units of the slope, units of the rate constant, which tells you it's zero order. The other one is that if you have a straight line with concentration versus time, it's got to be zero order. So this is a zero order reaction. Like most enzymatic reactions in your body are zero order. So we have to pick the integrated rate law here that matches. And so that looks like this. Concentration of A is going to be equal to minus KT plus concentration of A naught. So we're given everything that we need. We have minus, and the K value is the negative of the slope, which is 3.2 times 10 to the minus 3 molar per second, times time, which we said is 5 minutes. Very important that our units always match up when we do these calculations. And because our time in our rate constant is in seconds, we better convert our 5 minutes into seconds, which is 300 seconds. Plus our initial concentration, which is 1.5 molar. And this gives us negative 0.96 molar plus 1.5 molar is equal to 0.54 molar. So that's the concentration that will remain in this reaction. And I guess I kind of picked a bad spot. It's probably actually going to be more like there is 5 minutes when it's like 2/3 done. But yeah, you get the idea. So the trick here, you got to use the right integrated rate law, and you got to use information that's given from the question to figure out if it's first, zero, or second order. So what we're looking for either is units of the rate constant. Sometimes we just outright tell you what the order is, and sometimes you have to figure it out from the graph. So this gave you two ways of finding it. Either one will work.
Would it be theoretically good a graph, or just tell you like concentration, or like this is concentration of that, never mind.
Yeah, so we could give you any combination of those. So you do need to be able to look at a question and be able to figure out from what we give you what the order is. And once you select the order, then it's just doing the calculation.
Yeah, it's pretty easy. It's just,
Yeah.
yeah.
Does that make sense for everybody?
I tried these maps, so I had multiple choice, just multiple choice.
All right, online people are happy. How many do I got now? I got 11 viewers. Wow, doing great.
Oh, there it is.
Now we got an easy one. Well, not easy. They're all, I don't know. Often, actually, the grades, if you look at the grades on the multiple choice, they're lower than the grades on the calculation ones. So,
Yeah, it's because a lot of the time like, they give you more than one option.
because yeah, sometimes more than one looks good. It says, which statement is true? Unimolecular elementary reactions can be second order. No, unimolecular are always first order. They kind of mean the same thing. Unimolecular technically means one molecule is involved in the rate determining step collision. B, reaction intermediates are unstable and can never be isolated. That's not true.
It's gonna be seen, I guess.
Sometimes they're unstable, but sometimes they're not. By definition, if you look at the potential energy diagram that we often draw,
Aren't they usually stable? You will be able to like see it happen those like instantaneous ones?
yeah, sometimes they're very short-lived. They don't live very long, but sometimes they can live a long, long time. By definition, they are at the bottom of an energy well, right? They're down here. Transition states are unstable and can never be isolated. They're the peak. It's downhill in all directions.
That's what it is.
But intermediates, they're okay. So it's not B. Catalysts provide reactants with more energy. They do not. They provide a new pathway with lower activation energy. They don't give energy. They just give a new path. The rate of a reaction will be very rapid if the activation energy is small. That's correct. The smaller the activation energy, the faster the reaction becomes. Assuming you have good enough concentration, because it's also not only a function of rate constant activation or rate of reaction, but also the frequency of collisions, which is related to concentration. You know, because the rate is equal to K times the concentration of A times whatever. So like K gets higher the smaller the activation energy is, but you need a fast rate, you also need A. But yeah, that's the correct answer. Increasing the temperature will speed up a reaction by decreasing the activation energy. Temperature does not affect activation energy. It just affects the number of molecules that have enough energy to get over that barrier. And it also increases the number of collisions. Temperature does two things. But it does not decrease, like it does not lower the activation energy down. Okay, 15, we have an energy profile diagram. Label the axes. So this is energy, sometimes potential energy. And the other axis is progress of reaction. Sometimes you use time, but progress of reaction is more correct. Okay? The position of the reactants, so the reactants are over here on the left and the products are over here on the right. Intermediates are at in between the peaks. They're the valleys in between. Transition states are the tops of the mountains. And we give them these little double dagger symbols to indicate where those are. B, indicate the activation energies. So for each step, there'll be an activation energy which goes from where you start to the top of the peak. Over here, there'll be another one. Like that. And this one will be over here. So that's an EA, that's an EA, and that's an EA. 3 activation energies. The overall enthalpy change. So I'm going to use a different color here. That. The difference in energy between the reactants and products is your overall delta H. And state whether it's endothermic or exothermic. Products are lower in energy than the reactants, so energy has been released from the system. It's gone down in energy. This one is exothermic. Okay. Where are we at here? I think we finished B. Yeah. Third one is how many steps are involved. So count the transition states. Each transition state is a step. So this has 3 transition states or 3 peaks, so it's 3 steps. Yeah, the rate determining step is the step that has the largest activation energy, which is step 2. RDS, rate determining step. Sometimes also called rate limiting step. They mean the same thing. I always liked these questions when I was a student. They're like, I don't know, I found them easy to pick up points on. Plus, I don't know, you can't really like make an error here. Like you can't put this kind of question into your calculator wrong.
Or into Acorn, huh?
Yeah, or into Acorn wrong. 16, below is a proposed mechanism for depletion of ozone in the upper atmosphere. These two steps won the Nobel Prize in 1978, I want to say. Sherwood, Rowland, and Molina. I don't know. You can read all about that later. It was determined to be the reason why our ozone layer had been depleting. And okay, so we have two steps, and it's pretty straightforward. Identify the catalyst and the intermediate. Catalyst is something that's present at the beginning, is involved in the reaction, and is also present at the end. So usually it's consumed in an early step and then regenerated in a later step. So that would be Cl. Cl is the catalyst. And the intermediate is ClO. The intermediate is sort of opposite. It's something that's produced in an early step and then consumed in a later step. It's not there at the beginning and it's not there at the end. So ClO2 or ClO is produced in the first step and then is used up in the second step. (17) Pressure of a gas is 645 millimeters of mercury. This is just unit conversion, or converting gas from millimeters of mercury to these other units. The way I would look at this would be, we want to convert it to kilopascals. I would say we have 654 millimeters of mercury multiplied by 101.3 kilopascals per 760 millimeters of mercury. The conversion factors between all of these and atmospheres are given on the front page of the exam. So these aren't numbers you need to memorize. And that gives 87.2 kilopascals. B, we have 654 millimeters of mercury. In this case, we want it in atmospheres. So that's 1 atmosphere over 760 millimeters of mercury equals 0.861 atmospheres. And C, 654 millimeters of mercury times, in this case, 1 bar, that's 1.013 bar over 760. 0.872 bar. No problem. Easy peasy. 8. We have a small bubble rises from the bottom of a lake where the temperature and pressure are 4 degrees Celsius and 3 atmospheres to the water's surface where the temperature is 25 and the pressure is 0.95. Calculate the final volume of the bubble if its initial volume was 2.1. So here's what we have. We have sort of our T1 is 4 degrees C. And generally speaking, we want these in Kelvin for our calculations, for gas law calculations, which is 277 K. We have our initial pressure that we're given, which is 3.0 atmospheres, and we're given our initial volume, (2.1 mils). And then we're told it rises to the bottom of the lake where we have a new temperature, which is 25 degrees Celsius, which is 298 K. We have a new pressure, and they want to know what the new volume is. So how do you do something like this? Well, the way I do it, I know there's a whole bunch of formulas that involve PT and V, and maybe some of them are in your exam and maybe some aren't. You only need one. The only one you need is PV equals nRT. I'll go like this. PV equals nRT. Or P1 V1 equals nRT1. So what we're going to do here is we're going to make the assumption here that the bubble has the same number of moles of gas before and after. When it rises up, we're not changing n. So n is constant. So that means n equals PV over RT, or N1 equals P1 V1 over RT1, and 2 equals P2 V2 over RT2. And if N1 equals N2, we can say P1 V1 over RT1 equals P2 V2 over RT2. We can cancel the r's because they appear on both sides. And we now have this formula which relates the PV and T before to the PV and T after. And look what we have. T1, P1, V1, T2, P2. What's V2? So really, all we're doing here is taking PV equals nRT, assuming the moles don't change as this bubble rises up, and then we can get this relationship. Okay, so let's do it. P1 V1 over T1 multiplied by T2 over P2 equals V2. I just rearranged it. I brought some stuff over from the right side. And we stick our numbers in. We get P1, which is 3.0 atmospheres. V1 is 2.1 milliliters. Our T2 is 298 Kelvin. Our T1 is 277 K. And our P2 is 0.95 atmospheres. Atmospheres cancel. Kelvins cancel. And we get 7.1 milliliters as our answer. Great. On to 19. These are all the gas law ones still. The air in a hot air balloon is heated to 80 degrees Celsius, which inflates it to a pressure of 748 torr. If the pressure drops to 736, what is the temperature of the air in the balloon? Assume the volume of the balloon does not change. We also kind of have to ignore the fact that a hot air balloon is a big hole in the bottom. We're going to assume that all the gas that's in there at the beginning is still all in there at the end. Okay, so we're going to assume that N1 equals N2. So we're going to assume that V1 equals V2. And the only things here that are changing are pressure and temperature. So I'm not going to go through this whole derivation, but last time, remember, we arrived at P1 V1 over T1 equals P2 V2 over T2. If V1 equals V2, this simplifies to P1 over T1 equals P2 over T2, thank you. And it kind of gives us everything that we need. At T1, we're saying the temperature is equal to 80.0 degrees Celsius, which converting to Kelvin is 353.2 K. The pressure was equal to 748 torr for P1. Then we go to a new temperature, T2, we don't know, and we said the new pressure, 736 torr. So calculate for T2. We could say if we take this equation down here, and we rearrange that, we can say that T2 equals P2 over P1 times T1. Just a little bit of algebra there to get us to that spot. All right, time to stick some numbers in. P2 is 736 torr. P1 is 748 torr. T1, 353.2 Kelvin. And this gives us 347.5 Kelvin as our new temperature, which is 74.3 degrees Celsius. So it cooled down a little bit.
74.
Yeah,
Oh,
two.
yeah, sure.
It was at 80 and it went down to 74, which makes sense because the pressure went down by about the same amount, like just a small amount. We're halfway for time, and we're close to halfway for content. We'll get there. Don't worry.
What time is it now?
What's that?
What time does this thing
4.
Oh.
That's when it's scheduled to end. I'll finish it. Don't worry. But 4:30 is the eclipse, right? So we'll get out by then. A compressed gas cylinder containing 2.41 grams of methane. I see mass, I think moles. Has a volume of 3.30. What is the pressure in atmospheres if its temperature is 48? So this looks like a straight up PV equals nRT. But they gave us mass instead of moles. They give us the volume. The pressure is what we don't know. The temperature is 48.0 degrees Celsius, but we always want this in Kelvin. So I'm going to, on the fly, convert that to Kelvin. And the moles, we said we don't know, but we have mass, which we can convert to moles, which is 24.1 grams divided by 16.04 grams per mole equals 1.50 moles. So PV equals nRT. P is what we don't know, so P is equal to nRT over V equals 1.50 moles. R is, what's R? We got a bunch of R's, don't we? We got to pick the R that matches our units of pressure. So, I don't know. They want the pressure in atmospheres. So we'll use the R that has atmospheres in it from the front page of the exam, which looks like this, 0.08206 liters atmospheres per mole K. Our temp is 321.2 Kelvin. Our volume was 3.30 liters, and that gives us 11.98 atmospheres, which, if you look at all the numbers we're given in the question, we kind of have 3 sig figs for everything. So let's round that to 12.0 atmospheres. All right, onwards and forwards. A gas mixture contains carbon monoxide, argon, and hydrogen. What is the total pressure of the mixture if the mole fraction of H2 is 0.350 and the partial pressure is 0.480 bar? So this is kind of one of those Dalton's partial pressure kind of questions. And the relevant formula is this, that the pressure of a gas of like H2 is equal to the total pressure of everything present times the mole fraction of that gas. And what it wants is the total pressure, wants this, and it gives us this and this. So our pressure total is just our pressure of H2, our partial pressure over our mole fraction of H2. And our partial pressure is 0.480 bar over 0.350, which is the mole fraction, which has no units. It's not too bad. What's that?
If you go for the finish writing this next.
Oh, okay. All right. So we're just about to move to question 21. Just checking up with online people. We're up to 9 viewers, or down to 9.
You know that.
That's not bad. I suspect the views after this is online will.
Yeah, probably. Feel less than one to one.
Yeah, if there's like 3 questions you don't know, you're not going to sit for 3 hours for 3
If
questions.
you want this one, be able to like skip ahead and questions they already know are already done or something.
Exactly. All right, question 22. A mixture of 3 gases has a total pressure of 1.56 at 298. The mixture is found to have 2.5 grams of CO2, 3.4 grams of CO, 1.50 grams of argon. What's the partial pressure of argon? So we're going to use the same formula. Mole fraction of argon. Pressure total is provided, but we don't know the mole fraction of argon. The mole fraction of argon, though, is going to be the moles of argon divided by moles of argon plus moles of CO2 plus moles of CO. So if we have the moles of those 3 things, we're off to the races. And we actually have masses for them all, and we know how to get moles from masses. So we just got to go through the work here. The moles of CO2 is the mass of CO2, which is 2.50 grams, divided by the molar mass, which is 44.009 per mole, is 0.0568 mole. Our moles of CO are 3.40 grams, divided by the molar mass, which is 28.01 grams per mole, 0.1214 mole. Finally, we have argon, and that is 1.50 grams, divided by 39.95 grams per mole, 0.0375 moles. Great. So let's solve for our mole fraction of argon. 0.0375 moles divided by 0.0375 mole plus 0.1214 mole plus, that's that one, and then finally this one, 0.0568 mole. So when you do a long calculation like this, where you get a number like this and you feel like a sense of finality, and you want to type that number in, but you got to think about what the question's asking you for. It doesn't want the mole fraction of argon. It wants the partial pressure of argon, right? What is the partial pressure of argon? And so the partial pressure of argon is equal to the pressure total times the mole fraction of argon, which is equal to, I think we have it up here, 1.56 atmospheres multiplied by the mole fraction, which is 0.174, equals 0.271 atmospheres. And I think we have 3 sig figs for everything. Yeah, it's 3 sig figs is a good place to stop. All right. Question 23. Methane reacts with steam to give synthesis gas, syngas, a mixture of carbon monoxide and hydrogen, which is used for blah, blah, blah. Here is the equation unbalanced. What mass of hydrogen is formed if that much methane is converted to synthesis gas? First order of business is we got to balance this equation. So if you look at our carbons, there's 1 on each side, so carbon is already balanced. Oxygens, you have 1 on the right and 1 on the left, so oxygen is already balanced. Hydrogen, you have 6 on the left and only 2 on the right. So to balance this, all we really need to do is put a 3 in front of H2, and then we're all set. All right, so what we're going to do here is figure out how much hydrogen we get. We're going to get the mass of H2, and we're going to get that from the moles of H2, and we're going to get that from the moles of CH4, which we're going to get from the volume of CH4. So volume can be converted to moles using PV equals nRT. And then we use our stoichiometry to get moles of hydrogen, which we can convert to mass of hydrogen. All right, so let's start out. We wanted to find out the moles of CH4 that we started with. That's going to be PV over RT. So that's just a rearrangement of PV equals nRT. And the pressure it's telling us is 1 bar. The volume is 275 liters. R, the value of R we need to use is the one that has bar in it. So we would look on our front page. We don't just randomly pick an R, we pick the one with the right units, which is 0.038314 liter bar per mole K. And the temperature, which is 0 degrees Celsius, don't put a 0 in there though, because you can't divide by 0. We need it in Kelvin, which is 273. And that will give us the number 12.011 moles. So the moles of H2 is going to be equal to 3 times the moles of CH4. That's just because of the stoichiometry of 3 to 1 equals 36.033 moles. I realize I'm carrying too many sig figs. We'll round it off at the end. Take care of it at the end of the question. Okay. So now what? We have moles of hydrogen. That's not really what it asks for. It wants mass of hydrogen. So again, on the exam, double check every time you do a calculation and you feel like you're at the end. Double check that what you've calculated is what the question is actually asking you for.
Well, usually the units will be at the end.
Yeah. Often, the units are often given right there in the question. So make sure the units you have calculated are those units. Yeah, so mass is molar mass times number of moles. Molar mass of hydrogen is 2.016 grams per mole. It's just H2.
You don't gotta worry about
Yeah. Yeah, we took care of the 3 in front already up here. That gives us 73.2 grams. Common mistake would be not balancing the equation first and remembering to multiply by 3. It's probably the biggest one. Or putting in your moles at the end, not converting it to mass, not doing that last step. 24, true, false. Which of the following is true? Ideal gas law tends to become inaccurate at high temperatures and low pressures. It's actually low temperatures and high pressures. Both situations force those molecules to be close to each other. And when they're close to each other, what happens is the volume they take up starts to become important. And the other thing that happens is intermolecular interactions, IMF, start to become important as well. So no, it's not A. It's possible for a gas to be cooled below minus 300. That's below absolute zero, so that's also not possible. Dalton's law of partial pressures states the total pressure exerted by a mixture of gases is inversely proportional. No, Dalton's law is that the total pressure is equal to the sum of the partial pressures. Volume occupied by the molecules is always negligible. Not true when you're at low temperatures and high pressures. Kind of have E by process of elimination, but let's see if it works. At constant temperature, the pressure of a fixed amount of gas will increase when the volume is reduced. Yeah, that's Boyle's law. So yeah, if you increase the pressure, the volume will go down. You can compress a gas. So yeah, the answer is E. 25. The combustion of pentane produces heat according to this equation. How many grams of CO2 are produced if that much heat is released? Whenever I see these thermochemical kind of equations where we're mixing delta H and stoichiometry, I always think of that delta H as being like a reactant or a product. And if it's exothermic, that amount of heat is a product. So I would write this as C5H12 plus 8O2 goes to 5CO2 plus 6 waters plus 3510 kilojoules of heat. That's the way I think of that. All right, so it wants to know how many grams of CO. Nice thing about these balanced equations is everything's proportional. So what I do to answer a question like this is I would say how many grams of CO are produced. Stoichiometry doesn't really give us grams, it gives us moles. So let's first find out how many moles of CO2, and then as a next step, convert the moles back into grams. Mass mole conversion. So I just set it up like this. Ratio, we know that 5 moles of CO2 produces 3510 kilojoules of heat. That's the ratio that we have in this equation. And so what we want to know is how many moles do you get if you have this much, which is what, 25000 kilojoules? No, I put too many zeros. It's just that. So X here, like if I get rid of that question mark and put X, equals 5 moles over just that. Now what we want to do is convert those moles back into grams. So the mass will be equal to the molar mass times the number of moles, which is N. The molar mass of CO2 is 44.009 grams per mole times 3.56 mole is equal to 157 grams. Wonderful. How's your stamina for more chem? About halfway. Good. Because we're about halfway through. We're a little past halfway, actually. Okay. 26. A system contracts from an initial volume of 15.0 liters. When I see initial volume and final volume, I think like V1, V2. Under a constant external pressure of 0.800 atmospheres, calculate the work associated with this process. All right, work. Work is equal to what? Minus pressure external times delta V. Our delta V here goes from 15 liters to 10 liters, so it's contracted, so it's minus 5 liters. Or 5.0 liters if you want to keep all our sig figs intact. And it gives us our pressure of 0.8 atmospheres. So work minus 0.800 atmospheres times negative 5.0 liters equals positive 4.0 liters atmospheres. We don't really like units of liters atmospheres. We typically use energy in joules. So we need to convert a liter atmosphere to a joule. And lucky for us, on the front page of your exam, there's a conversion factor between liters atmospheres and joules. So you can find that on the front page. Basically, work is equal to 4.0 liters atmospheres multiplied by 101.3 joules per 1 liter atmosphere. So if you get a work question and you end up with liters atmospheres or liters bar, go to the front page for a conversion factor. This gives us 405.2 joules, which is kind of a more normal unit. The value here is positive. That means work is done on the system, which makes sense if the system is contracting, which it is. It's going from 15 to 10. It's being worked on to compress it. So I always think at the end when I get an answer, does the sign of this make sense? Right? It's always a good last check before you hit submit. Question 27. Calculate the work when 7.2 grams of PCl5 reacts completely according to the following equation. So work, again, is minus pressure external times delta V, which kind of looks weird compared to this question, right? Because this question gives us temperature and masses in a balanced equation. It doesn't give us any volume or pressure. However, one thing that we know is that PV equals nRT. So we can actually rewrite this as minus delta N RT. And delta N here is referring to moles of gas. So we're starting from a solid and we're converting that solid into a gas. So we need to get our change in the moles of gas. Okay, so to do that, we need to get our moles of PCl5. We start with a mass 7.20 grams divided by 208.24 grams per mole equals 0.03457 mole. Carry an extra sig fig. And now what we want is moles of gas produced, which is the 10 Cl2s. So the mole of the Cl2 is going to be the moles we started with of PCl5 times the coefficient 10 divided by the coefficient 4, because of the balanced equation coefficients. And that's going to be equal to 0.0864 moles. So that is our delta N. That's our new number of moles of gas that are produced as a result of this reaction. So our work then is minus delta N, which is 0.0864 moles, times R, and work is in joules, so we're going to use the R that has joules in it. Times the temperature, which is 32 degrees Celsius, which is 305.2 Kelvin. And the number we get is negative 219 joules. Negative means the system is doing work on the surroundings, and that's typically the case when the system expands. So it has to push the surroundings out of the way, and that's why the value here is negative. Okay, you can think of it as the system is losing energy by doing work on the surroundings. The surroundings here are expanding. Great. 27, done. Another sheet, complete. Question 28. A piston in Mr. Mo Dynamics car expands, doing 645 joules of work and releasing 225 joules of heat. What's delta U? That's just Q plus W. The whole trick here is identifying the correct sign for each of those two. So Q, we're going to say, is the heat, 225. It's negative if the system releases heat, and it's positive if the system absorbs heat. In this case, it's releasing heat to the surrounding, so it's exothermic, so it's a negative number. W, same thing. If it's doing work on the surroundings, work is negative. And it says it's doing that work to the surroundings, so that means it's going to be negative 645 joules. Sum them together, and you end up with minus 870 joules. And that's your answer for this question. The whole trick here is correctly identifying the signs of Q and W based on whether the system is expanding and doing work on the surroundings, or compressing and work is being done to it, and on whether heat is released to the surroundings. It's exothermic, negative. Yeah.
What is that the 3 next to the negative 870?
Joules.
The J.
Yeah. Pardon my handwriting through all this. My handwriting's not good at the best of times, and is worse on an iPad, so
Yeah, I was like, is that a 3? Yeah.
I'll start over. J. Yeah. Question 29, which is true? Delta U is positive when a system absorbs heat. So if it absorbs heat, Q is positive, and work is done on it by the system. W equals positive. The sum of those will be positive, so delta U will be positive when that is true. So yes, all that checks out. Instant cold packs feel cold because they involve an exothermic reaction. No, exothermic gives off heat. N2 has zero entropy at 0K. If it was a perfectly crystalline solid, that would be true, but it's telling us here it's a gas. So no. Gases have entropy greater than 0. Entropy is a path function. No, it's a state function. Since melting is an endothermic process, the temperature of an ice cube will increase when the ice cube melts. No, the temperature is constant during a phase change. So yeah, A is the correct one. You got it right on the first try anyway. It's always good, though, to read the other ones in case there's another one that sounds good. Because sometimes maybe you weren't so right on the first one you jumped at. 30. I like the funny names they come up with. Smarty Pants decides to invent an instant cold pack to quickly cool his beer. If the beer has an initial temperature of 18.2 degrees Celsius and a mass of 115, and the cold pack removes that many joules of heat from the beer, what will be the final temperature? This is going to be a Q equals MCS delta T kind of question. And they're giving us Q. So what we can say at first is that Q is going to be equal to negative 1125 joules. And I have it negative because the cold pack is removing that much heat. Okay, so the cold pack is gaining that many joules of heat, but the beer itself is losing. So Q of the beer will be negative because it's releasing heat to the cold pack. Q beer, I guess we'll say there. So what will its delta T be? Our delta T of the beer is going to be Q over MCS. And the Q is negative 1125 joules divided by the mass which is 115 grams, times the CS, which it gives us 2.46 joules per gram degree C. Just thinking about this question, I know these numbers were made up because beer is like 95% water. So its specific heat capacity has got to be close to that of water, which is 4.18. So like this is a made up number. But anyway, hopefully that doesn't like ruin the magic for you on this particular question. But anyway, that's the truth. That's negative 3.97 degrees Celsius. That makes sense. It's going to cool down. That's what we expect when we put a cold pack on the beer. So our delta T is our final temperature minus our initial temperature, and that equals minus 3.97 degrees Celsius. And we could say this, I guess, we could rearrange TF is delta T plus initial temperature, which is negative 3.97 degrees Celsius, and our original temperature was 18.2 degrees Celsius, which is 14.2 degrees Celsius. Great. Cool it a little bit. 4 degrees colder. Liquid nitrogen would do a better job. 31. For which of the following equations is delta R of reaction, delta H of reaction equal to delta H of formation? Another way of saying this question is which of the following is the correct equation for formation? Formation is the process of making a substance from its pure elements in their standard states. So what we're looking for on the left are reactants that are pure elements in their standard states. We don't want something that has two products either. We're looking to make just a single thing on the right, single substance. A is no good because we have ozone, which is not the standard state of oxygen, which is O2. B is no good because it has two products. C actually looks pretty good to me. Xenon gas.
Would xenon react?
Xenon can react with fluorine. Nobel Prize in that work for, I believe, a Canadian at McGill. Or maybe it was UBC. I might have that wrong. But yeah, there are examples of noble gas compounds. They're not very common, though, and they're not very stable. But you can make it, and both fluorine and xenon are in their standard states, which is gases. Let's check the other one to see what was wrong. This has a compound. That's not a pure element in its standard state, so that's no good. And the last one has carbon and oxygen to CO2, but carbon, its standard state is graphite, not diamond. Okay. All right. 32. We're getting there. A metal Batman figurine with a mass of 28 grams is heated to 95.8 degrees Celsius, then placed in a coffee cup calorimeter filled with 123 grams of water at 27. After some time, the temperature of the water is found to be 28.8. Calculate the specific heat capacity of the metal. Gives us the heat capacity for water. Assume no heat is lost to the calorimeter or to the surroundings. It's a very idealized situation here. And what we can say here is that the Q of the metal, of the Batman, let's say Batman. Q of Batman is equal to minus Q of the water. The Q of the water is MCS delta T. The mass of the water is 123 grams. The CS is provided 4.18 joules per gram degree C. And the delta T, notice it warmed up from 27.0 to 28.8. So it has a positive 1.8 degrees Celsius, 925.45 joules once you cancel out all of the units there. All right. So the Q of the metal, Q of the Batman, I guess, is the negative of that number, 925.45, because what was gained by the water was lost by the figurine. And what are we actually trying to calculate here? Trying to get the heat capacity of the metal. We have its Q, and we have its final temperature. So we're going to say that that for the metal is equal to MCS delta T. Its delta T is TF minus T initial, and its final temperature, I assume, is the same as the water. And its initial temperature was 95.8, which is negative 67.0 degrees C. All right, so we know the mass, we know the Q, and we know the delta T. The only remaining unknown is CS, which is what they want us to calculate. So our CS is Q of Batman divided by mass times delta T equals minus 925.45 joules divided by the mass, which I think we said was 28 grams. Times the delta T, which is negative 67.0 degrees Celsius. Luckily, the negatives cancel, which is important because CS cannot be a negative number. We need a positive result here. And the number I got was 0.493 joules per gram degrees Celsius. (33) 10.1 grams of calcium oxide is dropped into a styrofoam coffee cup containing 157 grams of water at 18 degrees C. If the following reaction occurs, what temperature will the water then reach? Assume the cup absorbs only a negligible amount of heat. And so what we're going to be doing is dissolving that calcium oxide, and we want to be able to get our delta H from that. No, we have delta H. What we want to get is the temperature. So the way we get temperature is from the delta H is using the equation that Q is equal to delta H times N. That delta H times the number of moles is going to give us Q. And to get moles, mass over molar mass, which is 10.1 grams over the molar mass provided, 56.08 grams per mole. Yes, question.
Is it for coffee cup volumetry is MCWT, but for volumetry is just CWT?
Yeah, that's right.
And didn't we do MCWT in the last question?
Yes, that was also coffee cup.
Oh, okay, I thought I said it was bomb.
Yeah, bum's coming up, but yeah,
Oh, okay.
yeah. We often use, MCS delta T is for the coffee cup ones usually. Okay, so Q is equal to our delta H, which is negative 64.8 kilojoules per mole, multiplied by 0.178 mole, gives me negative 11.53 moles cancel kilojoules, which is the same thing as minus 11.530 joules. Convert that on the fly, multiply by 1,000. That's because CS is always in joules, and we want to make sure our units always match up. So that is the Q of the system, which is the CaO. The Q of the water, which is the surroundings, is going to be equal to the negative, the Q of the system, which is equal to positive 11.530 joules. Q of the system is the reaction itself, the calcium oxide. Q of the water is the surroundings, in this case. The water is going to be absorbing all the heat that was given off by the system. Okay, so that's good. that Q is MCS delta T. And what we're actually trying to calculate here is the temperature the water will reach, which we're going to get from delta T. So delta T, just rearranging this, is QW over MCS is 11530 joules over the mass of the water. Actually, not the mass of the water, the mass of the solution. So what we actually have to do when you do these coffee cup calorimeters is think about the whole solution as being what's absorbing that extra heat. And what we have to do is take that 157 and add to it the 10.1 grams. So our actual mass of solution here is going to be equal to 167.1 grams. That's the common mistake. For any of these solutions where you dissolve something in water, people will just look at the water and forget that it's not just water anymore, it's now a solution. There's a bit of an assumption we have to make, which is that the solution heat capacity or specific heat capacity is the same as just pure water. But that's a better assumption to make than just ignoring that extra 10 grams we've added to the solution. So the CS becomes 4.18 joules per gram degree C. And if you calculate that, you should get the number 16.5 degrees C. This is delta T, so this is another situation where you just finished a big calculation and you want to just put the number in and move on. Think about what it's asking. It's not looking for delta T, it wants the final temperature of the water. So our final temperature, TF, is going to be equal to our initial temperature plus whatever the change was. The initial temperature was 18.0 degrees Celsius, provided in the question over here. We have to add the change to that so that our final temperature is 34.5 degrees Celsius. Next, we move on to question 34. 10 away. A bomb calorimeter has a heat capacity. Here's the bomb everyone's been asking for. Heat capacity, capital C, no small s, is equal to 2.18 kilojoules per K. A 0.176 gram sample of gas with that molar mass is burned in the calorimeter. The temperature is increased by 2.12 K. Calculate the enthalpy of combustion of this gas. So it wants delta H. We're going to get delta H from Q over N. And so we're going to do our calculation from the calorimeter to get Q. That's going to be equal to capital C times delta T equals 2.18 kilojoules per K. Our delta T is 2.12 K, which is 4.62 kilojoules. So that's Q. Now we got to take Q of the reaction. That's the Q of the calorimeter, by the way. So this is like how much the system warmed up. The reaction itself, negative of the Q cal, right? Because the reaction lost that energy and the calorimeter gained it. Okay, so you could say that delta H is Q system over N, or negative Q surround over N, which is the same as negative Q cal over N. So whichever way you want to do this calculation, it doesn't matter. But we have to recognize that if this reaction caused the calorimeter temperature to go up, it must be exothermic, and our final delta H value must be negative. So however you find it easiest to keep track of the minus signs, please make sure you do. So the Q reaction will be negative 4.62 kilojoules if you want to think of it that way. So our delta H, Q reaction over N. N, what's N? Well, N we have to actually calculate. Let's do it over here on the right. I'll do it in purple so we know it's kind of a different calculation. We're provided with the mass and the molar mass, which right away should ring bells in your head that we're probably going to have to use those numbers to get moles. 0.176 grams divided by 28.0 grams per mole gives us the value 0.00629 moles. All right, so let's use that down here. Minus 4.62 kilojoules divided by 0.00629 mole equals minus 734.4 kilojoules per mole. That's probably way too many sig figs. I guess everything we are given is 3, so let's just make it minus 734 kilojoules per mole. That way our sig figs will match up with what we're expecting. The number is negative, which is good, because this is an exothermic reaction. We want it to be negative because we know it's causing the calorimeter to warm up. So just keep an eye on those signs. That's an easy way to go through a lot of work and still get it wrong. Question 35. How much energy is required to heat that much water from a liquid at 65 degrees to a gas at 115, recognizing that this is water which undergoes a phase change at 100 degrees Celsius, right? It's provided here, the boiling temperature of water, which you probably know anyway. So what's going to happen, and with these kinds of questions, I always find it best to draw a little diagram where you're going to start at a temperature of 65 degrees Celsius. This is temperature, and this is like heat added. And let's say this is like, I don't know, 100, and this is like 115. You kind of have these three zones, A, B, and C, and what we have to do is calculate Q for each of those zones, and then add them all up. So zone A and C are Q equals MCS delta T calculations. And then B is going to be a delta H equals Q times Q over N calculation. So sort of combining the different kinds of calculations that we're doing in this unit, which is, I think, unit 3, the thermochem unit. So for zone A, I don't know why I tried to draw that as a delta, but it's an A. Q is MCS delta T, and the mass is 36 grams. CS, by the way, we're in the liquid phase here and we're a gas up there. So you pick the CS for the liquid, 4.18 joules per gram. Those should be degrees C here, not just C. It should be degrees C. An error on this. And delta T is going from 65 degrees to 100 degrees. So it's warming up by 35 degrees Celsius. When you do these calculations and you have delta T, this is like the one time we don't actually convert degrees to Kelvin. Because if you just add 273 to that 35, you're going to get a huge number. So you can add absolute temperatures, you can convert everything from Kelvin. You can turn the 65 to Kelvin and the 100 to Kelvin. But delta T's, you can't just add 273. Make sure delta T's, they're the same number whether they're in Kelvin or degrees C. and you calculate that, you get 5,267 joules. I'm going to do C now because C has the same calculation. Still the same old 36 grams. Now we're in the gas phase up here, so we have to use the CS for the gas. And our delta T is going from 100 to 115. So that's a 15 degrees Celsius increase there, which is 1085 joules. Now B is actually the phase change part. The temperature is constant at 100, and that's where we're going from liquid water and we're converting it to gas phase water. And once the last drop is converted to a gas, at that point it starts to warm up again and the temperature increases. So for part B, Q is going to be equal to delta H times N, and we have delta H VAP provided to us, but we don't have N, right? Well, we can get N, no problem. It's mass over molar mass, because they do give us the mass, which is 36, and water formula, we can get the molar mass for that. Which maybe you've done water enough that you even know the number. Anyone know water off the top of their head? Yeah, it's like 18 or 18.02, which is 2 moles. So our Q there is going to be equal to the delta H that's up here, 40.7 kilojoules, times 2.00 moles equals 81.4 kilojoules. So that number is like huge compared to the other two, right? C is like 1 kilojoule, and A is like 5.3 kilojoules. So the total, QA plus QB plus QC, is, let's convert them all to kilojoules as we do this, 5.3 kilojoules plus 1.1 kilojoules plus 81.4 kilojoules is a total of 87.8 kilojoules. So when you think about that, when you're doing these kind of heating phase change things, the biggest part, the biggest consumer of energy is doing the evaporation step. I don't know, when would that be important? Maybe like when you do laundry, and let's say you use hot water, you have to put energy in to heat the water up when you do your wash, but then you have to dry it. The drying takes a ton of energy because you're doing a phase change from a liquid to a gas in that situation. Way more than heating something up. Although I guess in a washing machine, you heat up a lot more water than you end up drying off because the volumes are pretty different. So I don't know. You can think about it. Question 36. During volcanic eruptions, hydrogen sulfide gas is giving off. So this is using Hess's law. We're going to be combining reactions to get an overall reaction. So this is the overall reaction that we don't have a delta H for. But we have standard delta H's for the component reactions that maybe we can combine to give you the upper reaction. So the first thing I would look at is look for reagents that appear in those separate reactions that appear in the overall reaction you see up top. First thing I see in this reaction is 2HS, H2S. And then I look in this next one, I see 2H2S as a product in the bottom. So what I would want to do is have that reaction flipped so that the 2H2S is on the reactant side. So if I flip it, I get 2H2S plus SO2 goes to 3S solid plus 2 H2O gas. And when you flip a reaction like that, you have to flip the sign of the delta H. The other one, you can see there's, in our overall balanced reaction, that little thing there, the 3S doesn't appear. So we want to be able to cancel that out with the other reaction. And we have S over there, but we only have one of them. So what we would like to do is take that second reaction and triple it so that we can cancel our S's. So if we triple it, we get 3S solid plus 3O2 gas goes to 3SO2 gas, and this becomes 3 times negative 296.4. If you add those together and start canceling stuff, the solids go. That cancels with one of that to leave 2. And what we end up with is the actual balanced reaction that we're trying to get to, which is good. So our delta H for that overall is going to be equal to minus 146.9 kilojoules per mole plus 3 times negative 296.4 kilojoules per mole. And if you add all those up, you should get the number negative 1036.1 kilojoules per mole. That makes sense? Everyone's with me? Good. We're down to 4 online viewers with a total of 30 people who hopped in and out. Well, if you're still with us online, thanks for sticking it out. We're on question 37, which means we have 7 more to get done. Use the bond enthalpies D provided to get an estimate for delta H of reaction for the following reaction below. 2 BR liquids, and this is the one where we dissociate everything. We break every bond to make atoms and then put all the atoms back together to make products. So basically we look to see what bonds are present in our reactants and products, count up all the energies, and then take reactants minus products, which is reverse for how we do every other kind of equation like this. It's always products minus reactants. But for this one, it's the other way around. So what I'm going to do is start out with our reactants. Br2 has a Br-Br bond, and we have 2 of those, and that's 193 from the table. Next, we have HCCH. If you draw the Lewis structure for C2H2, which is again from first semester, remember that, that's the structure of C2H2, and that has 2 CH bonds, that's in the table, so 2 times 414 for the CH, and we have 1 times C triple bond C 837 for the CC. Reactants done. Products. C2H2Br4 looks like this. That would be the Lewis structure for the product C2H2Br4. And so what does that have? Well, it has CBr, and it has 4 of them. Okay. It has 1 times, that's the CBr. It has 1 CC. CC is 347. It has 2 times 414, and that's the CH. Is that everything? CBr, CH, and CC. And then we can say the overall delta H is the sum of the bond enthalpies for the reactants minus the sum of the bond enthalpies for the products. And so that is equal to the products, reactant, sorry, 2 times 193 plus 2 times 414 plus 837 minus the products 2 times 414 plus 1 times 347 plus 4 times 276, and that equals minus 228 kilojoules per mole. So here we have a reaction that's predicted to be exothermic. Using this method to calculate delta H is very approximate. It's not nearly as good as using enthalpies of formation, except the problem with enthalpies of formation is it only works if you have those numbers handy in a table. Any structure, whether it's made or not, whether it's been measured in a calorimeter or not, you can get these calculations and give a prediction. The other thing, and this is I'm going back into first semester as well, see that it's exothermic. I might have predicted that this reaction would be exothermic. And the reason is that sigma bonds are typically more stable or lower in energy than pi bonds because of better overlap. And in this reaction, we're getting rid of 2 pi bonds and making a bunch of sigma bonds. So that might be expected to be an exothermic reaction, which it was. All right. We're getting closer. 38. Which of the following processes is delta S a positive number, greater than 0? Silver chloride goes from a solution to a crystal. No. Crystallization decreases the number of microstates, so that's a positive delta S, sorry, negative delta S. Gas to a liquid. No, we know liquid to a gas has a big positive delta S. This is the other way around. Milk is added to a cup of coffee. So that's taking 2 solutions and mixing them together. When we mix things together, we make a less pure mixture. This would be a yes. Puddle of water freezes. So that's, again, a liquid to a solid. That'd be a no. And this one is going from 4 moles of gas to 2. That's also a no. Delta S is positive in situations where you increase the moles of gas. This is not increasing. If you had the same number of moles of gas on each side, it might be positive or negative, but it would be like close to 0. It wouldn't be very large either way. But this would be a definite large negative delta S because we're going from 4 moles of gas to 2. Okay. 39. Place the following in order of decreasing standard molar entropy. There's an error in this question too, and that's this part. Standard molar entropy applies to pure substances in their standard states. You can't have a standard molar entropy for aqueous solutions of things. So really, what this should read is not standard molar entropy. Let's just call it entropy of 1 mole of that stuff. Okay. So what we know is that solutions, when you dissolve something and split it into ions, that increases its entropy. So the highest entropy is going to be this one, because it's going to split up when it's dissolved into 4 particles. It's going to make 3 Li plus and 1 PO4 3 minus, 1 phosphate anion. In other words, we would say its Van Hoff factor is equal to 4. So it's going to have the highest entropy. Sodium fluoride is the next one, and it's there because it is aqueous. Because now we have sodium fluoride solid versus aqueous. When you dissolve it, its entropy goes up. So this can be the next highest. And the lowest entropy here is going to be sodium fluoride solid. calculate the entropy change of the surroundings when 1 mole of water freezes at 0. We're given the delta H of fusion, so this is a phase change. So for a phase change, we can say that the delta S of the surroundings is equal to the negative of the delta H of the system over the temperature that phase change happens at. And this is provided on the equation sheet for you, this exact equation, which I'm going to go ahead and convert our delta H to joules and use 6020 joules per mole divided by the temperature, which is 0 degrees, but we don't put zeros in, we put 273 Kelvin. And that gives us 22.0 joules per K mole. We're doing good. Got through a couple quick ones. 41. The temperature at which the following process reaches at equilibrium is the normal melting point for phosphoric acid. So this question gives us some thermochemical data, which is the enthalpies of formation and the standard molar entropies of this thing at 298. And from that, we can calculate delta H for that process and delta S. If we have delta H and delta S, we can calculate delta G. So what we want to do here is get our delta H first of this reaction, solid to liquid. So that's equal to the sum of the delta H's of formation of the products minus the sum of the delta H of formation of the reactants. Okay, so that's just going to be equal to the product, which is the liquid.
Isn't the H reactants minus one?
No, products minus reactants.
This one's really just
The only time it's reactants minus products is when it's bond dissociation energies, which we did a problem a few slides ago doing that. Yeah, so it's always products minus reactants for enthalpies of formation. Minus our reactant, which is the solid. And that gives us our delta H is equal to 12.7 kilojoules per mole. It's a positive number, means it's endothermic. That makes sense. We're going from a solid to a liquid. We know phase change is going from a solid to a liquid or a liquid to a gas. It's got to be endothermic. We can also get our delta S, and I guess for delta S, going from a solid to a liquid, we're also expecting a positive value. So that's going to be equal again to the sum of the S zeros of the products minus the sum of the S zeros of the reactants. And the product is the liquid, which is 150.8 joules per K mole, minus the reactant is 110.5 joules per K mole, equals 40.3 joules per K mole. Positive number, which we're happy about, so we're good. So the question is asking us, at what temperature does the process reach equilibrium? At equilibrium, our delta G is equal to 0. So what we can do is use our equation, delta G is delta H minus T delta S, and set delta G equal to 0. You can use it that way, or I think there's also a formula on your formula sheet that says for a phase change, the temperature is equal to delta H over delta S for that phase change. Of course, these are the same thing when delta G equals 0, and we know delta G equals 0 when you're at an equilibrium like a phase change. So this is the equation that you use, and it's derived from delta G equals delta H minus T delta S. Okay, so that's fine. The only other thing that we could screw up on here is by forgetting to convert our delta H into joules to match the unit of joules for our delta S. So that's equal to positive 12,700 joules per mole divided by 40.3 joules per k mole. And if you do that, you should get the number 315 Kelvin. Joules cancel and the moles cancel. And 1 over k is k. And that's where we get our temperature, where that phase change will be at equilibrium. So that'll be the normal boiling point, or melting point. Okay. We're doing good. That was 41. We are on to 42. Hold out on me, pencil. We've only got a few more questions. Calculate delta G of formation of ammonia, given that the delta G for the reaction of ammonia with fluorine is that. So basically, this is the number that we want, the enthalpy, the delta G of formation. And this is just using, delta G of reaction is equal to the sum of the delta G's of formation of the products minus the sum of the delta G's of formation of the reactants. In this case, instead of giving us all the delta G's of formation, it left one out, but it gives us the delta G of reaction instead. So it's the same kind of question, it's just kind of giving us a little bit different information. So it's telling us that minus 1539.7 kilojoules per mole equals, we're going to do the products first, which is 79.9. These are all kilojoules per mole, so I'm just going to be leaving the units out just to keep this a little cleaner. Plus HF, which is minus 275.4 multiplied by 6, because there's 6 HFs on the product side here. Now we have the reactants. There we have NH3, which is our unknown. So I'm going to call that delta F H NH3. And that's going to be times 2 because there's 2 of them up there. F2 gets a 0 because it's a pure element in its standard state. So the delta G of forming it from a pure element in its standard state has got to be 0. And then we just stick in our numbers, I guess. Well, we can do the math on that first piece. All right. So I guess why don't we rearrange it? We can just say that like 2 times delta F H NH3 is equal to 79.9 plus 6 times negative 275.4 plus 1539.7. And that equals negative 32.8 kilojoules per mole. So that means the delta F of formation of NH3 has got to be half that. Minus 16.4 kilojoules per mole. Great. How's everyone doing? We're very close to having this finished. These have a lot of busy work, these last couple of questions. They're not letting us off easy with like a multiple choice or something at the end. The next question says, calculate the delta G of reaction at 298 using the following information. So it gives us the delta H and the delta S, and it wants us to calculate the delta G using that information. So let's get to work. Our delta H, once again, it's going to be equal to the sum of the delta H of the products minus the delta H of the reactants. So on the product side, we have nitrogen, which should have a 0 there because it's a pure element in its standard state. So we just have the 12 waters really here to deal with. 12 times minus 285.8. And that's it for the product side. The reactant side has 4 times minus 133.9. Plus 5 times 50.6. And that's going to give us a nice big negative 3147 kilojoules per mole. Make sense? This is the reaction between hydrazine and nitric acid. Hydrazine is, I think, used to be used in rocket fuel. Very exothermic reaction. Our delta S, 0, is again the sum of the S0s of the products minus the sum of the S0s of reactants equals 7 times 191.6 plus 12 times 70.0 minus 4 times 266.9 plus 5 times 121.2 equals, I'm just fast forwarding through all the little steps here. I assume you can do that calculation no problem. Joules per K mole. Bring our units back from our table. Now it wants the delta G at 298. It's going to be equal to our delta H, delta S0 equals minus 3147,000. We're going to make that joules because it's got to agree with our delta S. Minus our temperature was 298. You can see that in the question. And then we're going to put in the value we got for our delta S, which is 507.6. Equals minus 3298000 joules per mole, which is minus 3298 kilojoules per mole, which is probably still too many sig figs, which is minus 3.3 times 10 to the third kilojoules per mole. Get her down to 2 sig figs, which I guess we could have used 3 sig figs, but 3.30 we'll say. We have one left. Only one left for today. Tomorrow, Kathy Marimbo will be going through the rest of it. So 6 straight hours of chem. Fun. Not straight. I mean, you had a break in between. You might have other exams. I don't know. I like to think it's just chem you're thinking about. Or it's where your heart is, right? For the reaction of methane with water to form CO2 and hydrogen at 298, delta H, okay, they're taking the legwork out of this one. They're giving us the delta H, and they're giving us the delta S, so we don't actually have to use those tables and put all that information using enthalpies of formation together. Above or below what temperature will this make the transition spontaneous? So above or below what temperature the first thing you should think of is set delta G to 0. Because delta G at 0 is, if it's negative, it's spontaneous. If it's positive, it's not spontaneous. So 0 is the point where it switches from being spontaneous to not spontaneous. So we're going to use delta G delta H minus T delta S. And what does that little 0 mean up there, by the way? Standard conditions. 1 bar, 1 molar. 1 bar if it's a gas, 1 molar if it's a concentration. These are gases, so we're going to be looking at all of these in bars. So we're going to set that equal to 0. And that means that T delta S0 equals delta H, and that our T is our delta H0 over delta S0 equals those numbers, 164,970 joules per mole. Remember, they always have to agree the units. So always convert kilojoules to joules if you're intermixing delta H and delta S. And then the other number there is 172.8 joules per k mole. And that gives us 955, that's an equals 955 Kelvin is our answer. So that question actually is very differently asked, but it's similar to a previous question where you were asked to calculate the melting point for a phase change using delta H and delta G. We kind of did the same thing and we set delta G equal to 0. That's because a phase change is an equilibrium where we don't really consider it spontaneous or non-spontaneous. Depends. If you add a little heat, it goes one way. If you take a little heat out, it goes the other way. It's right on the brink. Delta G equals 0, and you can do the calculation this way. All right. Are people...
So saying above or below was temperature was it's non-spontaneous or spontaneous, so...
Yeah, so the temperature at which, above or below, it's non-spontaneous is 955. And if you look at the number, delta S is a positive number. So if the temperature goes up, this part goes up, and that makes delta G negative. So higher temperatures than that will make it spontaneous. Lower temperatures will make it non-spontaneous. And that is the temperature where it switches, which is what this question's asking for.
Delta H is positive, delta S is positive, so it's going negative?
Yeah, because the delta S has a negative in front of it. Yeah, so the delta S, this does have a delta H that's not favorable, but the delta S is very favorable. And so if you crank up the temperature enough, the delta S part will dominate the delta H. Yeah. It'd be endothermic still, though, for sure. All right, folks, thanks for bearing with me. We finished 9 minutes early. As I said, this is going to be posted online, so you'll be able to check this out anytime before the exam. And yeah, stay tuned for part 2, which comes tomorrow. No problem.